Hi, I'm Arthur. I've been programming basically my whole life, and for the past few months I've been building AI bots. No, not the ChatGPT wrappers. I'm talking about funnier stuff. I built artificial ecosystems where digital creatures starve to death, capitalist market simulations, and game bots designed to destroy humans. In games, not in real life. But there's a problem. My super Tic-Tac-Toe bot is kinda mid. It's slow, and if I try to speed it up, it only becomes stupid. So today we're gonna fix it. Super Tic-Tac-Toe is basically a tic-tac-toe inside another tic-tac-toe. At first, you can choose any place you want to play, any of the 9 boards, any cell. Here, I choose the center board, center cell. My opponent then is forced to play on the center board. He picks the top right cell, so I have to play on the top right board. This continues. I play top left, my opponent has to go to the top left. It's a long game if you play it right. If you win a board, you win that cell on the main board. And if you are sent to a one board, then you can play on any board you want. So what are we gonna do? Let's first build a game simulation. Any programmer would see this and think,
That's Matrix. Let's use arrays of arrays.
not us! I made that mistake before. We are craving speed, so we are going to make the board tiny, and every operation will have to be as efficient as possible. The problem with arrays is loops. If we want to check for empty cells, we'll have to pass through every cell and ask it, are you empty? You'll ask that same question 81 times. There's a better way to work with this. It's called Bitboards. You might be asking, what's a bitboard? It's something pretty easy to understand. But before that, we need some theory behind. Every variable takes up space. A boolean, which is a true or false switch, is a 1 byte big, which is 8 bits long. You can imagine it as 8 zeros. An integer has 4 bytes, that's 32 bits. We'll be using the unsigned 16-bit integer. So we have a lot of zeros in a row. What now? We can use 9 of them to build a 3x3 square. And just like that, we have the size of a tic-tac-toe board. The other 7 zeros can go to the trash, we are not gonna use them. So, we call this representation a bitboard. But a single bitboard only knows if it's empty or occupied. So, we'll have to use 2 bitboards per board. One layer tracks specifically where player X has moved, the other layer tracks where player O has moved. Overlay them and you have the full game. So finally we have a tic-tac-toe board, but how many do we need? Well, there's 9 of them, plus 1 for the big board. We have 10 times 2, 20. Bitboards won't just help us to only store the whole game on 20 integers. They'll also let us find empty spaces and iterate through them instantly. First, we merge the X board and the O board with an OR operation. Then we negate the result. Now zeros becomes ones and ones become zeros. Finally, we apply an add mask to clean up the garbage bits, and that's all. We have a map of all empty slots instantly. Now, how do we loop through them efficiently? We have to use some tricks. We use a CPU instruction called CTS, count the zeros, which tells us exactly where the first available bit is. This way, we know where the first empty position is, and we can use the number of zeros to create a mask for the move. We'll do this small trick. This will erase the bit we just processed, letting us jump straight to the next one without wasting cycles. Once we have the position, we just use an OR operation to stamp our symbol X or O onto the board. And just like that, we played a legal move. So what are we waiting for? Let's get right into it. So yeah, the board was a little bit straightforward. I think the code was pretty easy to make, but yeah, I also got a lot of luck and... oh, well, you'll see. With this I recorded all the green moves, and that way we can look up on the table to see if we want something, like doing a transposition of all. Yeah, so it seems like it works. Oh well. Okay, so I found the dot, and it's right here. So, yep. Oh my god. I'm dumb. What I had before was this, but iterator is the number of zeros I want. So, yeah. And it works. So we have the board. Now we need the brain. For the brain, we'll use an algorithm called Minimax. I like to call it the ultimate overthinking algorithm, because, well, let's look at how it thinks. First, we'll look at the moves we can do, let's say 8 moves. Then, for each of those, the enemy can also make 8 moves. And for each of those, we can make another 8, and so on and so forth. It's a tree that grows exponentially. But here's the logic. We both want to win. Let's imagine winning gives me positive infinity, and winning for the opponent gives me negative infinity. I am trying to maximize the score, the opponent is trying to minimize it. So, the algorithm goes deep into the future, to the very bottom, the leaves of the tree. Let's say we find a move that makes us win immediately. Positive infinity. Obviously we want that. But the enemy sees that if he makes the move that leads to that state, he loses. He won't make that move. He'll pick something else. The strategy comes back up to the tree layer by layer until we find the best move available. But calculating the whole universe takes too long, so we use alphabetical ruling. Think of it as common sense. If I find a move that it's already greatly worse than a move I found earlier, I stop looking. I don't care what happens deeper down that path because I'm never going to choose it anyways. It saves us a lot of time. And the way to make it faster is sorting. Instead of checking moves randomly, we will quickly guess which one looks best and check those first. By finding a good move early, Alphabeta can cut off the bad branches much sooner. So let's finish the bot and let's see how it goes. So I think that the bot took me a little longer to make than I thought it would. Sometimes I did some stupid things. Other times I think that, well, you'll see. Well, let's see if with this we can do something. Wait, what? What? So, the standard Minimax usually has a fixed depth, but I added a timer to this one, basically iterative deepening. If the clock is ticking, it keeps thinking deeper. So, I mean, I did some other optimizations like only recalculating active boards, switching from debug to release mode, blah blah blah. Look, I have recorded more than 5 hours of recording footage. Nobody wants to see that. So let's cut it. So, the bot actually sees 10 million bars per second. It's enough for it to hit level 11 without sweating. Just for context, my previous bot was struggling to reach step 7, hitting only about 300,000 bars per second. So, it's a big monster thing. Now I'm going to show you a match. Originally I planned on recording them like a serious chess tournament. You know, some sophisticated and quiet. But that felt a little bit too boring, so instead I did something different.
Ladies and gentlemen, on this night the beast will meet its creator. And on this corner, the architect, the scientist, Arthur. And on the opposing corner, the enhancement, the project, the monster, Sapiens plus Minimax. After the ball stretched to the center, connecting the punch. A power move ball, Minimax is not backing down. It responds with a left hook. Launching Arthur to the left board. Arthur kicks back, he sends the AI to the corner, but the machine keeps it up. It sends Arthur to the top. Look at the strategy. Arthur is sending Minimax to empty space. He's cutting out the ring. The machine can find an opening. This guy is pouring enough Arthur's well. The result has been touched. The machine isn't affected at all. As it connects, a vicious uppercut kisses the AI to the corner and... Oh my god, the valuation is dropping. The machine is confused, but it doesn't stop calculating. He connects the first two lines in the corner of the board. He is dissecting the game. Minimax looks hopeless. After seeing stopping, he shifts to the right board. He connects two more lines. He surely wants to end the game early, but the AI doesn't back down. It hits a bunch and fires back. It also connects its first two lines on the opposing board. Arthur takes the center board. Arthur has taken the heart of the battlefield. The crowd is on the field, but the AI doesn't back down. It wins the open board. Arthur has two big boards connected. But wait a minute. Minimax not only blocks but also creates a connected line. He creates another opening. Arthur is on the ropes. Arthur goes for the pin. He pins the castle. Hold on! The valuation just tanked to the 1 billion. The AI from the winning moves. Arthur is trapped. He looks left. He is right. But there's nowhere to run. The AI is in sweating. The AI doesn't have a pulse. It just stares into Arthur's soul. The machine sends Arthur for a clear hit. It's knocking him. It's trying with his foot. Go ahead, it says. Take your shot. Arthur connects a line, but it doesn't matter. It's too little too late. Oh God Almighty, it's over. The creation has destroyed the creator.
Nice. So yeah, I spent days optimizing the code to the point I think it was best. Just squeezing every cycle out of the CPU and not doing anything unnecessary. I know, it isn't perfect, but I mean, look at the raw power. I pick up 14 million boards per second and an average of 10 million. It's actually pretty good. Now, a quick heads up. These numbers are on an M4 chip. It pushes the processor to the limit, so results depend heavily on your hardware. But it's still just code. It's Minimax, it has a Horizon, so I prefer you to try it. The code will be open source on GitHub, link in the description. If you enjoyed watching the video, hit that like button and subscribe. Thanks for watching.